Hi everyone, welcome to the Nuvoton Level 1 training. I'm Abby, Field Application Engineer of Nuvoton. Today, I'm going to introduce the WDT and WWDT function of our NuMicro M031 and M032 series. This is the agenda. We'll talk about feature, block diagram, and settings of WDT and WWDT. What is WDT and WWDT? WDT stands for Watchdog Timer, and WWDT stands for Window Watchdog Timer. They are a piece of hardware circuit in our system, and they are used to check if the system is still working properly. When it detects that the system is working abnormally, it will reboot or reset the system to recover it. This mechanism can prevent system from entering a further damaged situation. However, how does WDT work to check if the system is still good? It uses a timer to make it. A timeout interval will be set to the timer. Before the timer is timed out, the system should send a signal to notify WDT that the system is still working well. If WDT doesn't receive a signal from the system when time is up, it will tell the system that something is wrong. If WDT receives a signal from the system before timeout, it will reset the timer to start over. The checking will be done periodically to monitor system status. You can imagine that you have a watchdog protecting your home. Every period of time, you have to feed the dog. If you don't feed the dog in time, it will bark to notify you. For WWDT, it works the same way with WDT. However, there is a window for WWDT. It means that you have to feed the dog in a time window, not too early and not too late. If you feed the dog outside the window, it means something is wrong. Therefore, for WWDT, there is a specific time window that the system should send a signal. We have known how WDT works to protect the system. Here's the detailed feature that Nuvoton WDT function has. First of all, there's a 20-bit counter for counting. For the timeout interval, there are 9 selections for user to choose. When WDT detects something wrong, it could notify the system via a WDT interrupt, or wake up the system, or reset the system. Before resetting the system, you could add a delay period. The delay period will give system some time preparing for the reset. For example, to store some data before resetting system. Therefore, we also provide 4 selections of WDT reset delay period for user to choose. In addition, we support to force WDT enabled after chip power on or reset. Here is the clock source of WDT. You can choose either LIRC, HCLK divided by 2048, or LXT as the clock source of WDT. The register WDT SEL is used to choose the clock source. The value you write into WDT SEL specifies the clock source you choose. Besides, the register WDT CKEN is used to disable or enable WDT clock. Therefore, to get a WDT clock to work, you have to choose the clock source and enable the clock. As we mentioned before, WDT has a function to wake up the system from power down mode. Please notice that if you need to use this function to wake up the system, the clock source should be either LIRC or LXT. It is because that only LIRC and LXT keep working when system is in power down mode. From the block diagram of WDT, we could know better how it works. First, select the clock source and enable the clock. Then, the counter starts to count by the clock. The timeout interval is defined by the register, TOUT-SEL. The system will feed dog by writing RST-CNT register. It will reset the counter. If the system doesn't feed dog when timeout, WDT will trigger actions by the setting of WDT registers. It could trigger a WDT interrupt. It could trigger a wake up. It could trigger a reset. For the reset, if a delay time period is set, it will wait for a period before resetting the system. Via this graph, you can see how the WDT reset goes more clearly. The first line is WDT clock. The second line is RST-EN, which means if WDT reset is enabled. The third line is IF, which means if the flag of WDT interrupt is raised. You can see that the RST-EN is high in this graph, means WDT reset is enabled. When the WDT counter counts to timeout, the flag of timeout interrupt is set to 1. After IF is set to 1, it will wait for a reset delay period, which is TRSTD in the graph. During the delay period, if there is no action to reset WDT counter, it will set RSTF to 1, which means to trigger a reset afterwards. When RSTF is set to 1, WDT will reset the whole system. The reset would last for a period called TRST. In our BSP, we provide an API to set WDT. It is WDT Open. You can use this API to set the timeout interval, reset delay period, and whether to enable reset function or wake up function. In the example, it sets WDT timeout interval as 2 to the power of 14th WDT clock time, and set the reset delay period as 18 WDT clock time. Besides, both the reset and wake up are enabled. It means when WDT is timeout, it will trigger both reset and wake up. Since there is a reset delay period set, the wake up will be triggered first. Then, system will be reset after the delay period. In this table, let's check the first and the third columns first. The first column, U32 timeout interval, defines how many WDT clocks to timeout. The third column is the actual value of WDT timeout interval. We use T WDT CLK to represent the value of one WDT clock. Therefore, WDT timeout interval is equal to U32 timeout interval multiplied by T WDT CLK. Since we provide 9 selections of timeout interval, from 2 to the 4th power to 2 to the 20th power, the WDT timeout interval shown in the third column could be ranged from 0.417 microseconds to 27.307 seconds. This table shows WDT timeout interval and WDT reset interval calculated by different settings. The WDT clock frequency we use for this table is 38.4 kHz. All the values listed here are calculated by 38.4 kHz. Besides, except for timeout interval, if we have set delay time before resetting system, the whole WDT reset interval would be equal to WDT timeout interval plus the delay time, which the formula is shown in the second column. The fourth column, WDT reset interval, is the actual values calculated by the second column. From note 2 below, you can see that we provide 4 selections of delay clock to choose, which are 3, 18, 130, and 1026. By the delay clock you choose, the WDT reset interval differs. Take the first row for example. The WDT timeout interval is 0.417 microseconds. If the delay clock is 3, the minimal one, the WDT reset interval would be 0.495 microseconds. If the delay clock is 1026, the maximum one, the WDT reset interval would be 27.135 microseconds. Therefore, the WDT reset interval would be in the range from 0.495 microseconds to 27.135 microseconds. You could refer to this table to choose the settings of timeout interval and delay time by your requirement. Above is the introduction of WDT. Now, let's talk about WWDT. WWDT has below features. There is a 6-bit down counter and a 6-bit comparator. There are 16 selections of WWDT prescale counter. We only allow to set WWDT controller one time after chip power on or reset. Besides, software cannot disable WWDT or change any setting. This is because we don't want the setting of WWDT to be modified by mistakes during system abnormal status. WWDT and WDT share the same interrupt handler function. Like WDT, WWDT can trigger an interrupt or a reset. However, unlike WDT, the counter of WWDT can only work in normal run mode. It will suspend in other modes. The clock source WWDT can choose are LIRC or HCLK divided by 2048. The same as WDT, there are registers for clock source selection and clock enable. For WWDT, WWDT SEL register is used to select the clock source, and WDT CKEN register is used to enable the clock. Here's the block diagram of WWDT. First, the clock will go through a prescale to adjust the frequency for a WWDT counter. Then, the 6-bit down counter starts to count down from hex value 3F. There is a 6-bit compare value called CMP-DAT. It is used to define the range that is able to reload when feed dog happens. For example, if CMP-DAT is hex value to 0, it means that the window range is from hex value 00 to 20. In this window, if the feed dog behavior happens, it will reload the counter to hex value 3F. When the counter value reaches CMP-DAT value, the flag WWDT-IF will be raised. It also means that it has entered the window. If interrupt is enabled, an interrupt will be triggered. Feed dog behavior is done by writing the register RLD-CNT. When it is written, the counter will be reloaded with hex value 3F. When the feed dog behavior happens before reaching the window, which means the counter value is bigger than CMP-DAT value, a reset will be triggered. The same, when time is up, a reset will be triggered as well. Therefore, by this mechanism, WWDT can monitor if the feed-dog behavior happens in the defined window. If the behavior is abnormal, a reset will be triggered to protect the system. We use this example to show how WWDT reload counter and reset system. The reload window defined in this example is from hex value 00 to 20. When WWDT is set to 1, which means to enable WWDT, WWDT counter starts to count down. When it counts to the value of hex value 20, the WWDT IF flag will be raised. If feed-dog happens in the window, it will clear WWDT IF flag and reset the counter to hex value 3F. It continues periodically and the second feed-dog does the same thing. If feed-dog doesn't happen and the counter reaches 0, WWDT RF flag will be raised and a reset will be triggered afterwards. In this example, we're going to show you how WWDT handles if feed-dog happens outside the window. The first feed-dog happens inside the window. It reloads the counter and clears the WWDT IF flag. The second feed-dog happens too early. The WWDT IF flag hasn't been raised yet. It is outside the window. Therefore, WWDT RF is raised to show that it needs to do reset because something is wrong. Like WDT, our BSP also provides an API for WWDT. The API is WWDT Open. You can use this API to set the prescaler, the compare value, and whether to enable the interrupt. This table shows you the range of WWDT reload window by different settings. The reload window starts when the counter reaches the compare value and ends when the counter is timed out. The second column is the start time. The third column is the end time. Values in the fourth column are calculated from the second and the third columns. The start time would be the WWDT compare value multiplied by a WWDT clock time. Besides, since there is a prescaler, the time has to be multiplied by the value of the prescale, which is shown in the first column. Therefore, take the first row for example. The start time would be 1, the value of the prescale, multiples WINCMP, the window compare value, multiples T WWDT, the WWDT clock time. The value calculated is 2.048 microseconds. The end time would be the timeout value multiplied by a WWDT clock time. The same as the start time. It has to be multiplied by the value of the prescale as well. Since the WWDT counter is a 6-bit countdown counter, the timeout value would be 2 to the 6th power, which is 64. We also take the first row for example. The end time would be 1, the value of the prescale, multiples 64, the timeout value, multiples T WWDT, the WWDT clock time. The value calculated is 4.096 microseconds. After getting the start time and the end time, you could know that the WWDT reload window is from 2.048 microseconds to 4.096 microseconds. The following rows are calculated by the same way. You can refer to this table to choose what settings to use for WWDT. Above is the introduction of WDT and WWDT. Thanks for watching. You could subscribe our channel for more information. Besides, please do not hesitate to contact us if you have any questions.